takeaways. So overall, Chari is a inference time dynamic pruning method, which you can take any pre-trained model you want that's out there, and no fine-tuning or training required. You can just apply. And it will reduce your latency about 2 times on average, and also reduce your KV cache size by 20%. And it can be combined with other efficiency methods like quantization or group query attention. We recently put the paper on arXiv, and we are gonna release the code very soon as well. So I want to end with a couple discussion questions or future directions for thought. So one thing is, like, since we keep the cluster membership same after processing a few tokens, could this method work for even longer context length? That's an open question. And could we apply similar inference time only pruning methods for other architectures or domains? I think that's also a very interesting question. And there's like one very recent work along this direction, which is called token merging, which is also a purely inference time method, which tries to merge the similar tokens in images during inference for each like transformer block. And I find that work quite interesting as well. So with that, I'll conclude my talk. Happy to take any questions, and please reach out if you're interested in chai.
Think that each bit somehow extracts its own pattern and tries to learn different from different perspectives. One head might become through that even conceptual things like logical reasoning, another head might extract other patterns and such things. And in the end, they should help each other, right? So according to your results, this is really surprising because your someone claims that most of the hits are almost great. Two of the hits are almost the same. So which means that maybe they are redundant in the first place. And that's why the question said, why did they add all of these hits? So people that are not that useful or which are almost the same, why don't we remove them? And the other thing that I want to mention is that I'm not sure whether you tested these on batch inference, where in the batch, different prompts or different flavors. How can I say it? Maybe the first prompt is again something related to logical reasoning, but the second prompt is something related to multilinguality and these kind of things. So then the application of each head would differ. I mean, that's what becomes different.
That's okay. Yeah, that's a really good question. So going back to the first one, I think so. Based on the ablations we did, where we pruned all QKV, right? We remove all heads, and we actually see a significant accuracy drop there, like the 5% to 10% drop. So it seems like there's still some value having multiple heads, and that's been shown, and theoretically multi-head attention helps too. And I think like the redundancy seemed to increase in later layers. So like the earlier layers seems like it's still like each head is still doing a different thing. So it is still important. So going to the second question, for batch, we actually tested running a higher batch size. Batch size is not only one in our test case, but the thing is we can use batch size, higher batch sizes, because our number of clusters are the same. But for each request, we can have a different cluster head per batch. But since the number of clusters are the same, you can still execute that efficiently. It doesn't necessarily mean the clusters will be the same for different requests across the batch, but the number of clusters are static. So, and that makes it enough to compute that efficiently. I don't know if that makes sense.
The specific set of prompts, these two bits should be similar, and their attention scores are also similar, but for another prompt, then these two bits might become like, might get far away from each other.
Right. So the clusters are determined. Cluster membership is happening per request separately. Per request in the batch.
Like G2A, you have every group having the same number of heads versus in this one, you're proposing that instead of having same number of heads, you sort of decide how many heads to have based on some sample data.
Yep.
So do you
Yep.
think then instead of like how now models like Llama 3 are being pre-trained with G2A, if Chai could be adopted during pre-training, and that would itself like your overall model parameter size itself would go down?
That's true. You could apply it to pre-training as well.
And in the examples which you showed, like 2K samples, context length, right? So how many number of initial samples you had to wait for before you could determine the cluster membership?
Specifically here, we use 5.
So just 5 samples were included.
5 samples were enough. And I think that was also shown in like, wait, one of the plots here. Let me see, sorry, here, this one. Like after 5, the membership changes just flattens. So 5 was enough.
But and you still retain the values. So you have as many values as the original number of bits. It's only the QK merging which you're doing, right? Or you're merging all QK.
So I noticed you have some kind of clustering where you do the clustering first reorder and you actually have this feature. You combine them, right? Especially if you across multiple GPU or some like distributed inference. Do you see that as a challenge when you increase the number of paths or going back from the way the problem?
That's a good question. We haven't tried it on a distributed inference scenario where the model is partitioned. Guess I'll need to think about that a little bit more. But we tried mostly on a single GPU, but I don't know why that would cause a challenge though. Cost, it might introduce a little bit more like data movement cost. Yeah. Thanks. We have not actually tried pre-training with Chai, but you could actually try it. But I'm just saying, like, I think group query for larger models almost became like kind of a standard, I guess, but it still causes some accuracy impact. And sometimes like you don't know that accuracy impact until like you train the model. So you need to pay that whole training cost to be able to see the accuracy impact of it. And for models that are like trained for days and weeks on large number of GPUs, so you don't want to risk like causing like trying it, right? So I feel like inference time methods is preferred in that sense, that even a small accuracy impact, some might want to take it, some might not want to take it, but I see this being applicable for. Yeah. Thanks.
Should I also? Okay, great. So let me start off by telling you how, or considering how people use LLMs today, right? So on the left-hand side, I have listed all of your favorite LLMs. This includes your ChatGPTs, Anthropic, Llama, so on and so forth. And then I've represented the world to be on the right-hand side, right? Now, the way you interact with an LLM today, be it ChatGPT, is you prompt the LLM, you get a response. And I've shown this as a single shot interaction, but you can think of going back and forth multiple times, right? So you do multi-turn. And also you can think of using your RAG-based scenarios, Llama index, LangChain, and so on and so forth, where you have more information in context. But it's up to you as the user to then take this information and then perform some action with it, right? So you perform an action on the world and get some response. Now, this is a little abstract. Let me give you an example. Suppose you want to install CUDA on your machines, right? So you ask ChatGPT, hey, how do I install CUDA? And then ChatGPT will give you a bunch of bash command line instructions that you then go take this. And then you have to now run these commands on your command line, and then you get the response, which could be a CUDA installed on your machine, so on and so forth, right? The vision we had is, can we flip this around? Can we put the user on the left-hand side? And the LLM we trained to do that is the Gorilla LLM. So the way you're going to do this is you're going to prompt the LLM. The LLM is going to perform an action, and then it's going to analyze the reaction and then relay this response back to you, to the user, right? Now, why? Why do we want to do this? This is based on a single observation, which is that humans are good distractors. We are good discriminators. We are not good generators, whereas LLMs are good generators, right? So let me give you an example. If I give you two recipes for a cake, two different types of cakes, and I ask you which one do you like, you probably will go one or the either. But if I give you two pieces of two different cakes and ask you which one do you prefer, you can immediately taste it and tell me which one you think is more delicious, right? So humans are good distractors and LLMs are good generators. So let's use it in that fashion. And that's the vision here, where let the LLM perform an action on the world and you just discriminate the response and see if you like it or not and decide to accept it or not, right? So let me show you another concrete example. Many of us are machine learning researchers, and there's one thing we've all wanted in 2023, which is, can I get an A100 GPU in East US? Now, there's a few things we want the LLM to do. The first is recognize that East US is how Azure names its regions. If you are trying to access any of the hyperscalers, then AWS will be US East 1A, and similarly, GCP will be US East 1. So you first recognize, so there's an analysis of what the user intent is, which is recognize it's East US. And then if you are a retail customer like most of us, you also have quotas where you can't start an arbitrary amount of GPUs. You have to go and check, do I have quota for this in this particular region? So there's some reading of the state of the world. And once you recognize that, okay, I have quota to start the instance, you then start the instance, and then you relay the artifact back to the user. And the artifact here could be an SSH terminal for the user to log into and thus get the access to your GPU. Right? So this is one example as to how you can do that. And over here, we looked at an Azure view of the world to perform some actions. Now, the model that we have trained, we start off with some machine learning APIs, but today Gorilla supports about 60,000 APIs across your hyperscalers, CRM tools like Salesforce, ServiceNow, Datadog, and then Kubernetes and a bunch of finance APIs like Yahoo Finance, Bloomberg, so on and so forth. Now, before I go into how we do this or what helped us train this model, let me present you two quick examples, right? So the first one, here's a simple command line. All I'm going to do is ask a simple question. Gorilla, list all my GCP instances. Now, what the LLM is going to do is it's going to go and figure out, okay, here's a bunch of commands, and I'm going to pick one of these commands to then execute. So I've executed an API call to then show me what instances that I have running versus terminated, so on and so forth. Now, folks, the fact that we can do this should not impress anyone, right? An LLM could do this. We all knew that. We built a neat command line tool around it with colors. Great, right? But the point is, APIs are very fundamental. So here is an example where I used APIs to talk to your hyperscalers. And let me show you another example where I'm going to use APIs to actually do translation. So this is a simple example where if you have used chat completion to interact with some of your LLMs, instead of hitting OpenAI, I'm going to hit my own machine in Berkeley. Right? Everything else remains same. I'm going to use a Gorilla model instead of GPT-4, 0613, or your favorite nightly checkpoint. And I have a simple question, right? I want to translate from English to Chinese. That's it, simple. Can an LLM do this today? The answer is yes. But we all know, oh, it could hallucinate, you may not get the response that you want, so on and so forth. And oftentimes an LLM may not be able to do. Like if you ask an LLM, what's the stock price of Meta on June 11, 2023? An LLM cannot tell you that, right? So our goal is simple. Can we call APIs that help you do this? So in this case, for the translation case, I need an NLP API. And the API provider here is we're going to use the models from Helsinki NLP corpus, right? Like the Opus English to Chinese translation APIs. I get some interpretation of why we're doing this, and then a bells and whistles around the code that helps you go ahead and execute the code, right? So I'm going to do a simple Python exec, nothing too fancy. I'm going to take the code that my LLM generated, that the Gorilla LLM generated, and execute this call, and I'm going to have the translation, right? So this is the translation, hopefully, of what are the key differences between renewable and non-renewable energy sources. So I showed you two different form factors, right? So one was the command line example, where you spoke to your hyperscalers using an API that your LLM generated. And here's another example where you spoke to all the different, well, you used an LLM to invoke a translation API to then translate what you wanted. So this is the vision, right? So can we have your LLM perform actions, not just read, but also perform write actions across all the services and applications that you have? As for those of us who come from a distributed systems background, think of this as most of the modern web runs on microservices. How well can we make an LLM understand and interact with these microservices? So that's the vision. And so before I go on to the next step, I also want to impress upon you that this is not just research artifacts, right? So Gorilla, as a project, has already been deployed in multiple enterprises to date. We have been on the top of Hacker News multiple times. There's a very vibrant open source community. We have been across international and domestic media as well. But more interesting for us is different enterprises have taken the key recipes behind Gorilla and trained their own models, right? So here's an example where VV8 went ahead and trained their own Gorilla for serving GraphQL APIs. So this is one of the ideas where you can go and take this idea of, oh, can we have an LLM talk to APIs, and then try to customize it for your own set of APIs. So I would urge you to try it out, and you can also try out Gorilla locally by doing a simple pip install Gorilla CLI, and then it's published as a PyPy package. Okay, excellent. So that's the model, and hopefully, we have some feel of how it works, what it does. So how did we do this, right? So what were the key interesting academic contributions that enabled the Gorilla LLM? So the first is the concept of retrieval-aware training. Now, the big question back in 2023 was, how do you mix fine-tuning and retrieval? And this continues to be an interesting question today. Now, the wisdom of the crowd when we started the project was that fine-tuning, and I use fine-tuning generously to also mean RLHF, instruction fine-tuning, so on and so forth, LoRa, and all of your parameter-efficient techniques. So fine-tuning was believed to be used to augment the behavior of the model, right? So you're trying to like make the model not say harmful stuff. You're trying to make it answer in particular fashion. And retrieval was considered as a technique to introduce new knowledge to the model, right? So this is by retrieval, I'm referring to all your RAG-based solutions. What we found with Gorilla is that fine-tuning is actually remarkably effective at both retrieval and at behavior, right? So you can bake in the knowledge, and you can also teach the model how to how the template of the response that you want. But there's one big problem, right? You still need freshness of data. A model that's trained is not going to have access to new data, so you need retrievers, but retrievers are inaccurate, right? So accuracy is not the right phrase here. For retrievers, you consider recall at K. And so for most retrievers out there today, your recall at K, it depends on the data set, all disclaimers aside, is somewhere between 70 to 80% at K equals 3 or 4, which means that 1/5 to 1/3 of the time, your user experience is going to be bad because you're retrieving the wrong data, right? So what do? You need retrievers for freshness of data, but retrievers are not good. Your recall at K is pretty abysmal. So the solution is retrieval-aware training. It's pretty simple, right? So if there's one line summary of what retrieval-aware training is that you're asking your LLM to double check your retriever, right? So consider your off-the-shelf retriever, your latest and greatest. You can use any of your embedding techniques. You can use any of your indexing like HNSW, so on and so forth, does not matter. You're telling your LLM, can you please verify the retriever before you start using it in your context, right? So that you want one bit information, and this is implicit. You want the LLM to implicitly identify if your retrieved results have recall or no recall. So you're going to do this by introducing correct and incorrect retrieved results during instruction fine-tuning, and your goal is to make the model robust to low-quality retrieval. Now, there's a few more tricks, like how do you incorporate chain of thought, which is a different way to get the model to respond in particular fashion. But this is fundamental, and what helped us actually train the model to be robust to low-quality retrievers. Now, even though we train this, keeping in mind how do we make the LLM call APIs, we realize there's actually quite a powerful technique. So if many of you have RAG-based workflows, you can think of using this. So we also wrote the Gorilla paper, but there was another paper called Raft, a follow-up paper that looked at how do you use some of these retrieval techniques for more general purpose setting. So I would urge you to read the paper to learn more in this context. All right, slight change of gears. For the next idea, let me start off by asking an open-ended question. How much does GPT-4 hallucinate? Anyone?
Not as much as before, but it does.
Excellent question, excellent answer, right? Not as much as before. And whenever I ask this question, the responses I get is more, less, more than 3.5, less than 3.5, so on and so forth. Which brings us to an important problem, which is how do you quantify hallucination? Now, hallucination is ill-defined in a general purpose setting, right? So if I said Shishir wrote Macbeth, is that inaccurate or is that hallucinated? Shishir exists, Macbeth as an art exists, but I'm not Shakespeare, right? So it's very ill-defined. But I argue that for APIs, you can define that pretty well. And the way I'm going to do that is by borrowing this classical concept most of you might have learned in your undergrad called abstract syntax tree, right? So here's how I'm going to measure hallucination. First, let's take a simple API call. So this was the one that you saw in the Colab notebook that I showed you. And the first thing that I'm going to do is I'm going to build an abstract syntax tree out of this. Then I claim that given a snapshot in time, the set of APIs a service provider gives you is fixed, right? So across time, it may vary. But today, as of now, Stripe offers you K different APIs. And those are the only APIs you can call. You can't call more. You can't call, I mean, you can choose not to call a few of them, but that's the idea, right? So I'm going to build an abstract syntax tree of the set of all APIs that a service provides. And then I ask a simple question. Is the API that my LLM generated a proper subtree or not? And if it is, I claim it is not hallucinated. I make no comments on accuracy, right? All I'm saying is that this API exists. You're not going to get a 404 error if it's a RESTful API call, or you're not going to get a stack trace if you're trying to execute this API on your local machines. So that's the idea. Now, there's some implementation details over here that you have to be careful about. So, names of models over here, for example, are exact string matches. Something like temperature is a range match where it can be a floating point value from 0 to 2. And some stuff like optional pre-trained equals true is an optional argument. So you don't want to check for that, right? So this is, you may not want to check for exact matches over here. So, but the good thing is this is very easy to build, and we have open sourced all the tools to help you build these syntax trees for different services that you may have across multiple languages. So this is an idea. So let's try and see if you can use this as a metric to measure all the different models out there today. So on this graph, on the x-axis I have hallucination, and on the y-axis I have accuracy. One does not imply other, and let me give an example to illustrate this. Suppose I want to send $100 to Amir, right? I can use PayPal API. If the LLM says, hey, Shishir, you want to send $100 to Amir, please use the PayPal API to send money, that is an accurate API. He'll actually get the money, right? So then it's accurate. So your y-axis is good. But if the LLM said, use a PyTorch API, you really can't send money with PyTorch, right? So then it's an inaccurate API, but it's also not hallucinated. That API exists. On the other hand, if the LLM said use as plus API, then that does not exist, right? So then that's pure hallucination. So on the x-axis, you have hallucination. Of course, lower is better. And on the y-axis, you have accuracy. Higher is better. So you want to be on the top left corner. So this plot here shows zero shot, which is you have no retriever, right? This is how you talk to ChatGPT in the general purpose setting. You go ask a question, you get a response, and then you move on with it. So in the zero shot setting, what we show is that you can actually perform pretty well compared to both open source and more interestingly, closed source models as well. What if you use a retriever? I've shown a few examples here, but in the paper, we consider BM25 and a lot of your commercially off-the-shelf retrievers. So GPT retriever basically means we use text ADA 002v2, which was the state-of-the-art embedding technique. And Oracle retriever is where, at recall at 1 is 100%. So if God gives you the exact API, then what do you do? And what we show is that across different settings, across zero shot and all the different retrievers you may use, Gorilla either meets or beats the performance of closed source and open source models. And we did this for TensorFlow, PyTorch, and Hugging Face APIs in the paper, but a lot of people have gone ahead and implemented this for different finance APIs, hyperscalers, so on and so forth. So Gorilla is a training recipe where you can use this recipe to train models for different APIs for different services. Okay, now this is how do you make the LLM call an API? And this was the first part of the talk. Now for the second part of the talk, it's simple. It's a logical next question, right? Okay, the LLM invokes the API, but who's going to run it for you? And so over here, what we want to do is build a runtime for generating the calls that an LLM produces, right? So goal, simple, run the code your LLM generates. And we want to do this in such a fashion which is human out of the loop. Today, most systems out there are like, how do you have human in the loop? And I still believe that's the right way to go. But in the future, you might want to take human out of the loop because you start becoming the bottleneck, right? Well, okay, if you want to do that, what's tricky, what's challenging? Let me motivate this example using the simple Amazon shopping cart microservice scenario, right? So I have 4 different microservices over here. You can think of all of them talking to each other using gRPC or RESTful API calls. So a set of users come in. The first thing they do is they add an item to the shopping cart. And then you want to check out. When you do check out, there's a fraud detection service that runs. And then finally, it goes into inventory and dispatch, and you get the product delivered to your doorstep. Now, it should not come as a surprise if I argue that in the future, a lot of these microservices are going to be powered by LLMs, right? Either completely or partially in conjunction. Now, the problem with this is you're having an untrusted and non-deterministic system inside a trusted and deterministic ecosystem, right? So the problem with this is, suppose you place an order for a red marker and you get a blue marker because your checkout process got screwed. So what goes wrong? Well, first, the only information you get is delayed signals, right? If you made the wrong checkout, you don't get to know immediately. You only get to know downstream 3 days later when the user actually got the product. And second, only downstream signals are visible. You don't get to know exactly where in the pipeline was there an error that you can go back and diagnose because there are LLMs involved through and through, right? So what do you do? And our goal with building GoX, so GoX is the name of our execution runtime, is simple. Can we present abstractions and policies to let the LLM perform actions in the presence of delayed signals? Right, so I'm going to give you abstractions, and then you can define the policy such that your LLMs can now power microservices and applications and services that can now continue to run together with human out of the loop. So that's the idea. So to be more formal, the problems are you have delayed verification and only downstream outcome is visible for your set of distributed systems. And what we want to do is we want to guarantee reversibility for LLM actions, right? So suppose I send a Slack message to my collaborator. Then if there was no human in the loop, when I understand that something is wrong because they spoke to me about it, then I can go back and delete the Slack message, right? So that's reversibility. As most of you may be thinking, well, you cannot always do that. If I send an email, there's no reversibility for emails, right? So then what do you do? So in those scenarios where you cannot do reversibility, can we bound the blast radius, right? So you can specify and say, look, my email should only be sent to the people who report to me, not to the people whom I report to, right? To be more concrete, if you're an enterprise, you may want to specify and say every time an LLM is called, I don't want the dollar cost value to be more than 5 cents, either to my users or to my internal party. And then can we take this value, can we take this abstraction of dollar cost and then build policies that's now going to guardrail what action can or can't your LLM do? So that's the goal. So this is, and how do we do this? So there's a few interesting ideas. If you start looking at services, if you come down from, oh, what does Slack do? What does Gmail do? What does any of your banks do? It's intractable, right? So instead, can we go from a bottoms-up route? Can we classify the different services out there into 3 categories? RESTful API calls, right? This is your GET, PUT, POST request, your modern web, file systems, and databases. And then can we try and see how do we build these abstractions for each one of this individually, right? So for RESTful API calls, one example is, can I maintain state? Can the runtime maintain state and not the service itself? So if you're deleting an email, can Gorilla maintain state and keep a copy of the email locally and then delete the email? Needless to say, the problem with this is you're going to keep having multiple parallel forks of the universe every time you create an action, right? So how do you manage state is an open question. If you have file systems or databases, snapshots and versioning are classical systems techniques, except they're too heavyweight and too expensive. So then can you use interesting techniques like CRDTs and lattices to then go ahead and build optimizations, right? So one example is, if you order something on your Amazon shopping cart, you added something you added one item into your shopping cart. And if you want to undo it, rather than rolling back the transaction, can you add -1 of the item into your shopping cart, right? So assuming time is monotonically increasing and all the good properties that are required to implement lattices. So that's the idea here. Can we use some of the interesting techniques in theory and in systems to now bound the worst case scenarios for LLMs? And in those cases where it can be reversible, why bound? Let the LLM perform an action. You can always roll back when you don't like it. And how do you do this efficiently? So this was, I only presented some high-level ideas here in the interest of time, but I encourage you to check out our paper where we build a system that can actually do this for RESTful API calls, file systems, and databases. Okay, with that, I want to conclude by presenting some of the other interesting ideas as a part of the Gorilla project. So the Gorilla was initially an LLM model, but then it has grown on to be an umbrella of projects across the board, right? So retrieval-aware training and techniques to measure hallucination is what helped us train an LLM that can invoke API calls. But the idea of retrieval-aware training, which is you're asking your LLM to double check your retriever, was so powerful that we made that into its own standalone solution called RAFT, which stands for retrieval-aware fine-tuning. And finally, our idea of using hallucination of using abstract syntax trees to measure hallucination, we use this as an offline metric to compare and benchmark all the different models out there for function calling. So if you have k different models, and if you want to understand how do all of these models stand on calling functions across JavaScript, Java, Python, so on and so forth, then the Berkeley function calling leaderboard is a way to do that. And then Open Functions was released 2 months ago and continues to be the state-of-the-art Apache 2.0 licensed model to do function calling. And finally, the execution engine is a system solution to deal with all the shortcomings of LLMs, right? LLMs hallucinate, user intent is often not clear, there's always confusion on what's going on. So can we use reversibility and blast radius semantics to now have human out of the loop LLM systems? With that, I'll conclude. Thank you very much.
You want to add another service or new set of APIs? Is that another retraining or fine-tuning, or is that a RAG?
Yeah, so there's 2 ways to do that. One is if you want to add a whole new service altogether, you can either try to do fine-tuning, right? We're trying to say, well, here's my in-domain set of functions. How do I train the model to do this? Or you say, I'm not going to fine-tune the model. I'm going to use the function calling model. And to bake in the knowledge, I'm going to use RAG. Right? So use your RAG to now shortlist the top k functions, and you give it to the model. And the model's duty is to pick among the top k and fill in the right arguments and return the function to you. So it's two different techniques, right? And you can use either of those depending on the use, depending on how comfortable you are with fine-tuning.
So this might be an open situation, but the example which you presented for Amazon, right, like the end-to-end process. So in that, sending a wrong item is one example, and probably you can use cost to restrict on what kind of item is sent.
Right.
But similarly, if you also send an address, put an address to which it has to be sent to, right?
Yeah.
There are many things which can go wrong over there, from your apartment number to your zip code entirely, like even
Right.
a single digit here and there.
Right.
So how do you control that? Because that is a very fast pace. Right? How do you bring?
Yeah. So the answer is there's 2 ways to do it. One is very well understood, is how your mobile phones do it today, which is coarse-grained. You open an app, you give an app to your gallery or your camera, and the app has access, right? So when I opened Teams, I had to give access on my Firefox for it to use it. So you can say, look, if an LLM is ordering DoorDash, it's okay for the burger to go a wrong person's house, but it should not touch your Chase Bank API or stuff like that, right? So you can have very coarse-grained service level distinctions. The other way to do that is to use the reasoning capabilities of LLMs to request scopes or particular scope. So for example, you can say, I can only pick addresses from my address book, so on and so forth. And oftentimes when you have APIs, they come with scopes and permissions. So you can have like fine-grained scopes, and you can use the user as an ultimate source of truth. Yeah, so it's like, think of it as a spectrum. One is coarse-grained, well-defined, used in smartphones, used in laptops. The other one is more fine-grained, used for apps and services, hard to understand, and you can pick where you want to be on the spectrum. Yeah.
Like in terms of actually being able to this being in service, right, for Amazon or someone, they would also have to run this and see where the LLM is going wrong, and then define these scopes, right? Like because these scopes initially they might go with an initial with a set, but they will keep on learning. Okay, this is where it could go wrong. This is where it could go wrong. So do you see that itself might incur some kind of costs for them that they would
Yeah.
have to pay before they can actually deploy these services. They would say that, okay, a wrong item had been sent, it had been sent to a wrong address, and so on and so forth.
Yeah. So I mean, this is an opinion, right? So let me give you mine. I don't think that's the way you're going to go down. So you're trying to say, okay, let's have a scope and then start refining, because then you're giving no guarantees, right? So you're back to ground zero. Instead, what might happen is you're going to start with a very broad scope, quantify your damage, see at which point are you okay with it, and then you go for a deployment. So now every time you know you're screwed up, that's a damage that's already factored in, and you may then choose to narrow down, right? So that's a much better way because you have some semantics and some guarantees. Because you have an LLM which is untrusted, stochastic, and undeterministic. And these two are different actually. Stochastic means if you roll a dice, it's stochastic. But if you ask an LLM to roll a die, it can give you -1, which is undeterministic, right? Negative number. So you're taking this system, and on top of that, you're saying, oh, scopes can be random, which is not going to help, right? So you're going to use your scopes as a walled garden, and your LLM can choose to screw around, and then your damage is confined. Yeah.
Questions? So you're essentially executing code generated by the LLM, right? And in the codex paper, like OpenAI outlined a lot of issues and risks associated with that, and they're recommending sandbox environments to execute such code. How will you handle that?
Yeah, so sandboxing, so that's the first thing people think about. But the fact is, sandboxing works when you want to do things in isolation, which is not, so that's done, right? We understand C groups, we know how to do that well. But the point is, you want your LLM to change state that you care about. It could be a file system, like, oh, move file, etc. So in those scenarios, sandboxes don't really tend to help.
But the risk still exists, right? Like executing.
Correct. Absolutely. And so then the question is, what do you do? So for example, when you're doing file system operations, we try to initialize git or git LFS and then take a log and then you perform an action. And if the user does not like it, you can always git reset to a previous commit, or you delete your .git and you're good to go. So yes, but you see how a Docker would not have helped here, but using something like git semantics might help.
Docker's not the solution, but the risk still exists in this.
Absolutely. Yeah. Yeah. Okay. Thank you.
You can turn the camera as well. Just right. Thank you, everyone. So that's the end of our workshop. Thank you for all the great talks. Thank you for the great discussions, the questions. Thank you all the speakers. And thank you for the panel members. Thank you for all the, I guess, paper submissions and authors. I don't have much more to add here. We do have a mixer that will happen post-workshop, and you can collect the tickets, like the drink tickets at the door from the guy that's waving them. I do want to thank all the people that helped us organize the workshop, especially the reviewers. We had a pretty short time to review the papers due to the timing constraints. So thank you for all the reviews. They were very useful. And also thank you for all the organizers. It was mainly a work over, I guess, 3-4 months. So thank you for volunteering your time. And also, I would like to request if anybody would like to kind of help out in any of our organizing activities, please feel free to contact us. And also, if you want to provide us with any feedbacks on how we could do better or what you would like us to add in the workshop, please also contact us. I guess you can find us our emails on the workshop websites. And with that, thank you, and hopefully we'll see you again in the following workshop.